Okay, power factor correction. Let me grab my pointer here. All right. So the one who came guys through the program the proper way, we in the second semester that we teach you guys how to do power correction for motors and what's not. Today, this should be continuation what we have done in the second semester, Matt. So ELEC, you will be exposed to this one more time. So power factor correction, power factor big deal, like you heard about it before. If you go below 90, if you are a commercial industrial customer, like we're doing commercial industrial, you go below 90, you get penalized. What does penalized means? Your company will pay money for the electrical utilities because you are screwing up their system, basically. That's why it's a big deal, power factor. So let's talk about power factor. This presentation, guys, is two parts. One is going to do the theory about the power factor, and the second one is going to go directly into the calculation. So a few things, guys, about the power factor. Define what the power factor is, as why do we care. We're going to do the concept, use the concept of power factor or correcting for power factor. Then we need to do some correcting low power factors. How do you correct if you have a low power factor? There are two ways of correcting power factor, Adam. One way you guys are very familiar with, by adding bunch of capacitors. That's a capacitor, that's method one. Method number two, they add so-called synchronous condenser or motor. That's method number two. So we'll talk about these two ways of correcting power factor. Ideally, guys, we would like the power factor to be 100%. We cannot get 100% power factor. So what the utilities require you to do is to go between 90 plus. So to stay in the 90s for the power factor. So any comments, guys, any questions about what we're going to go, the define of the power factor, what the power factor, how to correct power factors with capacitors and motors. You guys, when you were, who taught you Derek Basic? Scott. So you talked about resistive load, inductive load, and capacitive load, right? And the perfect load that we like is a resistive load because most of the power that we put in that load will be consumed into our work. Unfortunately, not all the loads are resistive. Motors, for example, transformers and what's not, they're non-resistive, so they have coil on them. When you have a coil in a motor, guys, so I have the resistive load, the concept of resistive load, that's your resistor. Then we have also the inductive load. This is my R, this is my XL, the inductive load. And there's also the capacitive load, which is my XC. That's part of when you put a capacitor in the system. So Karen, when you connect any electrical load in a power system, this electrical load will have two components. The impedance of this load, they call it the impedance. The impedance is made out of three components. One of them will be the resistive, the capacitive, and the inductive component. All these components make the electrical load, and because of all this, guys, it will create a power factor, an angle between the current and the voltage, which if it's too large enough, it will screw up the power system. It will basically consume more current than pull more current than what it's consuming. Any comments, guys, about the impedance? You guys remember the impedance, the concept of the impedance equal the resistor? You know, we talked about the impedance, the concept of the impedance Z, when you take it equal R squared plus X L minus XC squared, and when you calculate the Z, when you did the AC analysis, so that's part of the concept of the impedance, which is R, XL, and XC. So the power factor, guys, is defined as the cosine, you're going to see in a second, of the angle between the voltage and the current. So Karen, if your current, the sine wave of your current, it looks like this, and the amp is also looks like this. So here's my voltage, here's my amp. This is 100% power factor. There is no angle between them. Can you see that? Everybody see that? This is 100% power factor. If your voltage looks something like this, and your current now looks something like this, now there's an angle difference between the two. That will create that angle, the Q. The cosine of this Q will create the power factor. So ideally, Karen, we would like the voltage. Can you guys look at this? Here's the voltage, here's the current. We would like them to be in sync, like this. If they shift slightly, we would like them to shift within 90%. So that little angle, the cosine of the angle, we want it to stay within 90%. If they're shifted too much, this means you are pulling more current than what you're consuming, who cares? Excel is going to provide you with all this current in their transformers and conductors, but you're not paying for it. So because of all of this, one power factor is a major concept. So the power factor, guys, the cosine of the angle between the current and the voltage. You see them. It goes from 0 power factor all the way to 100% power factor. That's a cosine, right? The cosine value between 0 and 1. 1 being perfect and 0 being bad. Typically, you don't have a 0 power factor, right? And the true power, the power factor is defined, power factor is always defined as a true power divided by the apparent power. So you go measure the current inside the conductor and the voltage, multiply by 1.73, that will be your apparent current, apparent voltage. Then go measure the watts with a watt meter, that will be your true power. Divide the two by each other, that will give you the power factor concept. Any comments, guys, any questions? I know you guys touched on that one in the second quarter, so this is, I don't want to go into the theory of it, but the power factor is the true power over the apparent power. What we want to take it from here, how to correct the power factor, okay? Okay, here's the angle. You guys took this one with Scott, do you remember that? I hope you remember a little bit. Here's my impedance, here's my inductive reactance, here's my capacitive reactance, the angle here between the resistive, this angle right here, guys, between the resistive and the impedance is called the power factor angle, or theta. So when you take cosine of 50, it should be to 0.781, which is 78.1%. Very bad power factor. The best power factor, guys, is when Z sits like here. Here's a Z. So basically, Z equal R. That's equivalent to 100% power factor. When Z sits here, here's my Z, which is Z equal XL. This is basically, that will be your 0% power factor, theoretically, your 0% power factor. Do you guys see that? The 0% power factor versus 100% power factor. So obviously we can't be 0. You'll never be 0. You can't be 100% because load fluctuates. We want to stay within what? 10% of the 100%, guys, which is 90% power factor. Any comments, guys, about the angle, the concept? And I don't want to go back into the basics, guys. And you know, you should have done that one. Matt will do a little bit more in terms of the angles and the calculation. But that's the concept of 100% power factor when Z equal R, and when Z equal XL, this is 0 power factor. Now, most of the time, Z, of course, equal what? Equal R squared plus XL minus XC, or XC minus XL squared. And that's most of the time you're at this situation, right? Where there's a Z, the Z has R, resistor, plus XL and XC. That's where, when you have a power factor like Dunwoody here, we have motors, we have lights, we have computers, everything else. So you'll have a mixture of the R's and the C's. That's the basic concept of power factor. Okay, now for you guys, now in the second year you're graduating, you're going to be taking the basic concept into reality and measuring the power factor. Measuring the power factor, now in this day and age, Karen, they have something called power factor meter. Power factor meter, when you guys in the in a drought switch gear, what they install is a meter, a digital meter. The digital meter can measure, guys, the voltage, the current, the watt, the VARs, the power factor, the harmonics. Almost every institution, every industrial commercial building right now you walk in, they will have their own meter to know what's going on in their business. So that meter, part of the measurement that digital meter there has, it will also measure what? Power factor. So if your power factor is 90 or more, you're good. If it's less than 90, what do you need to do? Go correct the power factor. Cool? So this is probably the method number 1 of power factor. Another method, guys, is you can find yourself, can measure the kilovolt, amp, and the watts. You have a watt meter, and you have a volt meter and amp meter, and you do the calculation and you find your power factor. That's not commonly used now. Because with the digital world, you can click and say, I want to see what the power factor in this institution. Yep, here's my power factor. You can actually, some of them guys are intelligent enough to tell you when your power factor fluctuates, send you an email. You can communicate with your meter. So that's why digital meter, Adam, is so important. So important. So that's method number 2, which is kilowatt meter. I'm sorry, kVAR, measuring the kVAR and the kilowatt and finding them. And there's a kVAR meters. Method number 3 is basically the watt meter or the kilowatt meter in combination. You have a kilowatt meter or kilowatt meter and voltmeter and amp meter. So you do the math. You basically do the math. So for this one, guys, the power factor will equal kilowatt over I times V times 1.73. So can I guys emphasize the proper way now of the power factor is a power factor meter, which is a digital meter that can give you everything. Can I have thumbs up, Chad? We understand that one? Now, but you'll get into all the institutions where they have the kVAR and the kilowatt meter. And I don't know if you guys remember a couple of chapters ago, we talked about how to read these and so forth. But this is the most important thing is you walk into a building and they know what the power factor in their building is. Why? Because if they don't, they'll be penalized. Okay. The power factor, guys, also is the angle between the true power. Here's my true power and my, this is called apparent power, my true power and my apparent power. The power factor here, which is, this is the R, this is the Z, and this is the XL. This is the reactive power. Reactive power, true power, apparent power, R, Z, XL. You guys called it, Derek, you called it the power triangle and impedance triangle when you guys in the first semester. Power triangle and impedance triangle. Same thing. Power triangle and impedance triangle are exactly the same thing. So here's my triangle here. Here's my true power. Here's my reactive power. Here's my apparent power. And the same thing, impedance triangle. Here's my Z. Z is here. You can see the Z. Here's my R, and here's my XL or XC. You can see it's the same thing, power triangle or impedance triangle, same concept. In this project, in this example, guys, they're giving you data. Here's the volt amp, and here's the watt, and here's the kVAR. And from here, and the relationship between these, if you guys remember, kVA equal, Pythagorean theory equal kW squared plus, what's the other one? kVAR squared. You square them to find the apparent power. So if they give you the kW, you square the kVAR, that will get you the apparent power. Any comments, guys? Any questions? So when you find the apparent power, then the power factor will be, my power factor here would be basically the true power, which is 796 K here, divided by the apparent power, which is 1075 K. Divide these two numbers and you will get yourself a 0.742. Any question, Adam? Any comments, any questions? Correcting power factor. That's how we did it. You guys did it in the second semester. What we're going to do correction is slightly different, using same concept, but using tables in a few seconds here when they do the calculation. So when you correct the power factor, Karen, your job is to neutralize this value, basically. How do you neutralize it? The way the kVAR, guys, there's a capacitive kVAR and inductive kVAR, and these are like positive and negative. Cool. So capacitive kVAR and inductive kVAR, they pull in different directions. So in order to minimize or neutralize the inductive kVAR from the coil, you add capacitive kVAR. So how do we correct power factor? By adding capacitor. So I have an inductive kVAR of 720 kVAR. If I would get rid of it, Adam, I just add a capacitive kVAR of 720 to neutralize it. Any comments, guys? Any questions? Any comments? Any questions? You'll see this one in a second here. Okay, so here's what they did. Look at this. I have my kW stays the same. I want to correct my power factor, guys. Here's my original kVAR. I subtracted, can you guys see that? This is subtracted take this, subtract 20, that will give you this value. Can you guys see that? Everybody can see that? You take the 720, so we took the 720 minus 200 equal 520. So we eliminate, neutralize 200 kVARs out of the kVAR system. Who cares? Then when your triangle guys get smaller, then when you do your calculation versus it used to be like this, right? Then when you do your calculation, this becomes 8 to 1. It goes lower. So your power factor becomes 796 divided by a smaller number is okay. And guess what? You got yourself a power factor, a higher power factor, which is in this case 97%. 97% power factor. So you reduce the angle. Can you guys see that? How you reduce the angle? You're reducing the angle. Any comments, guys? Any questions? Any comments? Any questions? Reducing the angles. The examples I'm going to give you guys, the application example for the power factor correction doesn't talk about the angles. It talk about the proper methods. Can I get you guys to understand the following? If you have a cap, a capacitor, the kVAR of the capacitor, and if you have inductor like I called, kVAR, VAR, these are like a black and white. These are opposite of each other, and they neutralize each other. So Karen, if I want to kill 100 kVAR or coming out of motors, coils, what do? You add 100 kVAR of capacitors. Did you guys hear me? Do you understand this concept? By adding kVARs of capacitors to kill the kVARs of motors. Any comments, guys? Any questions? Comments, questions? How to correct the power factor? We can't, guys, we correct the power factor by adding kVARs. So here's my power system here, and I went and I added 200. I added a capacitor. Here's my capacitor, and I tied it to my power system, and this is a 200 kVA. That 200 kVAR will correct the power factor to the value that we're looking at here. So that's my kVAR correction. Another method of correcting the power factor, guys, instead of adding capacitors, it's adding synchronous motors. Synchronous motor, guys, I don't know if you touched on them too much. We talked about them a little bit. Synchronous motors, they run at synchronous speed. So if you overexcite them, when we go to comments, you're going to see they talk about excitation of motors. They put DC in the coils, the armature. So they put DC in the stator, actually. They put DC and they overexcite them. They put DC on them to overexcite them. Long story short, if you overexcite them, they call it overexcited, they start actually generating kVAR, for you. So they act like a capacitor. Believe it or not, you add a condenser in your building. The problem is, this is a motor. The problem is no load on this motor, no mechanical load. Can I emphasize the word no mechanical load or electrical load in a motor? So if you have a motor, Karen, you walk into a building and you have a motor just spinning and the rotor, nothing connected to it. And you see, what the heck are they doing with this guy? So this is a motor that's correcting the power factor, a synchronous motor. Can I get you to understand that concept, guys? A synchronous motor can, in the building that we have, if you guys look at that one, we have a bunch of condensing motors. Can you guys see that right here? Two condensing motors to correct the power factor for the building that we have in the book. So that's what they do. They correct the power factor. They run them unloaded, then they overexcite them. They start acting like a capacitor. Instead of pulling, look at that. Instead of pulling kVARs, they start pushing kVARs. Done. That's all what you do. You push kVARs. Now you're acting, instead of pulling, you're pushing the kVARs. You're correcting the power factor. Okay, so that's how they do them. Using, they call them condensers. So on the test, there will be on your test, guys, how do you correct the power factor? Two methods: capacitors and condensers, or synchronous machines. This is how they work, Adam. They have some type of a power factor relay here, and when the power factor kicks in, they close. When you start that one, they close a couple of contacts. They run that motor, and they start exciting. I don't know if you guys can see. They put DC value right here. They put DC value from a DC machine, and that condenser, and they close these, run the contacts, and they run them They run them unloaded, no load. When I say unloaded, guys, there is no mechanical load. It's not a fan. It's just a rotor like this and rotating. Okay. This is a control system for it, so it monitors the power factor and corrects it. Any comments, any questions about condensers? They call them condensers, synchronous motors. Think of them as capacitors. Oh, the power factor will affect the branch circuits as well as the feeders.
Yeah, but how does it affect the branch circuit?
You're pulling more current. Out of the. I'll show you an example in a second. It affects the branch. If it's a branch circuit going to a motor, if it's branch circuit going to a light, not a whole lot. If it's branch circuit going to a motor and the power factor is 70, here's what happens. If a branch circuit, let me tell you how. Here's my motor. Here's my 20 amp. Say the power factor is, to make it easy, 70%. And if the power factor is 70%, right, then you're only using 7 amps out of, say, a 10 amp. This is a 10 amp motor. You're only, you're using a 10 amp, you're pulling 10 amps, right, but you're only using 7 amps out of them. What happened to the other 3 amps? They sit there and magnetize the system. So they're creating more voltage drop problem for you because you're pulling more current than what the load needs to compensate for the low power factor. That's the problem, is pulling more current than what the load needs. You know, the other current is just sitting magnetizing your system. So create a voltage drop problem. So if this becomes 100% power factor, say this is 100% power factor, then, and your motor is 7 amps, then you're pulling right now you're pulling 7 amps. 7 amps, and your motor is 7 amps, you're good to go. You don't have to pull 10 amps to run a 7 amp motor, roughly. Does that make sense? The difference between 70% power factor and 100% power factor on a 10 amp, on a 7 amp motor. So if it's 7 amp, you pull 7 amps and you're good to go.
So does that have an effect on the motor itself then when you're pulling that much?
The motor is the problem. The motor is the guy who is creating this.
Yeah.
No, the motor itself, no, it wouldn't. Voltage drop problem. Voltage drop. So that's the field that they do the excitation with, my friends. So that's my power factor. Here's how they do the condenser, guys. The project that we have, Adam, we have 2 condensers right here. You can see them right in here. They're coming in here. These are my correction. We're correcting up to 520 kbar, and I have a lagging amount of this. So look what happened. I have 720. You subtract from it 520 for, no, we're correcting, we're bringing a kVA, kVAR, we're going to bring 7, okay. So the lagging, okay, yeah, absolutely. So see, can you guys see this value here? You subtract these 2 values from each other, and you got yourself 200 kVAR. Now my triangle that I need to draw here has 200 kVAR and still have the 796 kW, and then that will get you an 821 kVA. So that's how they. Derek, look at this. Before we corrected the power factor, can you guys look at the amps here? The amps were 1293. After we corrected the power factor, our amps dropped from 1293 into a 1030 amps. Can you guys see the difference? After you correct the power factor right here, after you correct the power factor, before and after you correct the power factor, right at this point. Very, very important, guys. What stays the same, Adam, is the kW. Here's my kW here, and kW here stays the same. What changes when you add the capacitors? kW stays the same. The kVAR will change, and the kVA will change. We drop down the kVA, the kVAR, the kVA will change. As a result, the power factor will be better. The power factor will be better. So this example shows you what happened to your power factor when you correct it. What happened to your power factor when you add the synchronous machines. But Derek, you just asked a major question here. Do you see what happened? Look at the current. Can you guys see the current here? Went from 1293 amps in the feeder down to 1030 amps just by correcting the power factor. just by correcting the power factor. So major concept. That's why you get penalized. Major concept, that's what you get penalized, my friends. Okay, so that's why correcting your power factor. Any comments, guys? Any questions? Comments, questions? How do you correct these? Matt, you just buy that motor, stick it into with a wire and conductors and size them. We're going to size them in a second here and tie them to the system. That's how you correct your power factor. Okay, so that's basically the concept I want to talk about, guys. The concept of power factor. Any comments? Any questions? When you correct the power factor, you always, guys, get rid of the VARs, the kVARs. And I can't emphasize what happened to the amps. Look what happened to the amps, guys. The amps, the kW always stays the same. Can you see the kW always stays the same? The only thing that changes is the VAR. The VAR here was 720, it becomes 200, and then because the VAR changes, now I have also the kVA changes, and also the kVA will change. You know, because they are in the same equation, guys. So that's the concept of correcting power factor. The other concept that we're going to talk about, guys, is parallel conductors. You will talk about parallel conductors. When you parallel the conductors, all the conductors of the same circuit have to be the same conduit. 1, 2, 3, 4, 5. Phase A, phase B, phase C, neutral and ground of everyone must be the same circuit. Karen, you cannot parallel less than 1 aught. The conductors must be identical. To the conductors in the other group. If it's copper, the insulation have to be the same. The material have to be the same. The termination have to be the same. If you put them in a race wheel, the race wheel also have to be the same. These are the rules for parallel conductors. We added them here. When you parallel conductor, guys, the conductors cannot be less than 1 aught. Insulation the same. If it's material the same. All the conductors of the same circuit have to be in the same conduit. And if you're using conduits, it has to be the same. Any comments, guys, about parallel conductors? The reason why they do a parallel conductor because the capacitors here that we're having, they have 2 sets of 2 feeders. You remember, Derek, when we were talking about 2 sets of 4 conductors, blah, blah, blah. So these sets have to be identical. You guys know that. THHN, copper, the insulation type, and so forth. Okay. Correcting power factor with capacitor, guys. Capacitors, you are familiar with the capacitor, I hope so now in the second year, third quarter. So add a capacitor device leading. The capacitor creates a leading current, which is leading power factor. By adding it to the system, it counter effect the kVARs, the lagging kVARs that's coming out of the motors. And that's how it corrects the power factor. So the kVAR goes one way, the other kVAR, here's my cab, here's my motor, and then they neutralize each other. Measuring power factor, we talked about, guys, measuring power factor. You need a watt meter, amp meter. Typically, if you have a watt meter, and amp meter and voltmeter, you can calculate it, or you can have a var meter and a watt meter. A couple of concepts of correcting the power factor. If you have a correcting motor power factor for motors, when we correct them, guys, there are 2 ways of correcting the power factors. We're going to be looking at a couple of tables here, which we're going to be using. So watt meter and voltmeter. The horsepower. And for different type of frames, guys, will be connected to correct the power factor to this value. 973 is given. So the smarter than Chad, they told you if you have a motor, guys, this value, add a capacitor this value to correct the power factor. Offenders, when it comes to the power factor, offender number 1, guys, are motors, induction motors. If you solve the problem of the motor, so every time the motor comes up, a capacitor comes up with it. Now we solve the problem. That's what they're doing. So there's a bunch of tables, guys, for U-frame and P-frame motors. Different type of build motors. Based on these tables I'm going to show you, you can pick a capacitor to correct the power factor right at the point of correction. The next part of this lecture, guys, will be exactly what I'm going to be talking about is sizing the capacitor conductors. For conductors, Adam, we use a multiplier 135%. I'll show you from there. There's one little thing, if it's on the side of a motor, it cannot be less than 1/3 of the rating of the motor. Capacitor, connecting capacitor cannot be less than 1/3 the rating of the motor current if you tie it on the load side of a capacitor. Install the influence code requirement. We'll talk about these in a second here. Here's how they connect the capacitor, guys, for a motor. Look at that. You bring a wire from here and you tie it. If you do it this way, then you have to adjust the overload here. You have to adjust the overload based on the corrected power factor. There is no disconnect and there is no overconduction device. That's probably the preferred one. They go right on the starter and you add a capacitor. And this conductor cannot be less than 1/3 of the full load current of a motor. The full load current of a motor. That's my capacitor, the conductor size. Another way of connecting it, guys, is coming from this side. Can you guys see that connecting them? Then you have to size your disconnect 135%. The fuse typically 135%. The conductor that you need here is 135%. So these are what we're going to be calculating in a second, and then you tie into your capacitor to correct the power factor. Any comments, guys? Any questions? Comments, questions about correcting the power factor? Two ways. Can you guys see that? One on the load side of the overload, and the other one on the line side of the fuse, way on the line side of the overload too. In a case like this, you guys don't get involved in it. You do not have to correct adjust the power factor for the corrected current. The rest of it, guys, is testing the capacitors. You don't get involved in testing the capacitors. We have, when you test them, obviously for safety, disconnect and discharge the capacitor will give you, before you test the capacitor, you know capacitors, guys, did you guys do that in the high school? Give a little capacitor, give it to your friend, and then give him a shock. Capacitors store energy, so you have to discharge this energy. If it's a big capacitor, it could kill you. So most of the capacitors that they use in the power industry, they have a resistor. So when you disconnect them, they discharge all this energy to a resistor. Connect the terminals to an ohm meter. Then there's an ohm meter, guys, and high potential test for the insulation. All these are different tests. They test the dielectric material. What is a capacitor? Do you guys know what a capacitor is, right? Remember the old days? It's a metallic, say a copper plate here and a copper plate here, and in between them a dielectric material that does not conduct electricity. That's what a capacitor is. So if that dielectric material become too conductive, then it becomes it shorts or it opens, or there's a lot of issues with testing the capacitors. Anyway, you guys are designers, so you don't have to worry too much about that. But be aware that your capacitor have to be tested. If they're not working, this means they're either short circuit or open. So you have to provide a capacitor testers. All typically multimeters, Adam, they will test for the capacitors, the insulation of the capacitors. Different ways of testing. So that's basically what the power factor, guys, is. Correcting power factor to improve adding capacitors and inductive adding capacitors and a synchronous motor to correct the power factor. So I can't get you guys to more than understand that synchronous and capacitors will correct the power factor. We correct power factor typically to 100 to 90% or higher, not to 100%. Typically we don't do 100%. Okay, there's a couple of tables, guys, I'm going to be using in a second here. So I would like you guys please to look at them and see how you can use them. We talked about the angle, guys, the power factor. Here's the angle, power. Okay, here. Talked about synchronous machines and how it works. Okay, this is probably the most important concept, guys, and we talked about it. And Adam, I cannot emphasize what happened to the current, guys, here and after. I can't emphasize, guys. Look what the current happened to the current. I want you guys to look at this value here before you correct it and after you correct it. Matt, 796 kW, 796 kW. That kW would never change. Before and after stays the same. The only thing that changes, guys, the things that changes is the kVAR before and the kVAR after. Can you guys, the kVAR before and the kVAR after got reduced, right? And of course, the last thing is because of that, the kVA and my kVA also got reduced. Can you guys see that? The kVA and the kVA got reduced. I cannot emphasize the concept. Why did they got reduced? Because of this value right in here. This value right in here. And because of this, the current got reduced from 1293 all the way to 1030. That's what you guys are doing. You're adding capacitor to reduce the line current. Who cares? Voltage drop will become better when you reduce the current for the same amount of, guys, for the same amount of power, for the same amount of load, for the same amount of load that I need. I'm pulling 1030 amps versus before I was pulling 1293. That's why Excel gets mad at you. You're consuming, all what you need is say 1030 amps, but you're paying for this, but you're making it still give you this amount of amps. So remember, correcting the power factor is good for voltage drop, good for conductor, good for Excel or your company. Any comments, guys? Any questions about this concept? Probably this is the most important one. Instead of condensers here, you could have used capacitors too. Oops. Capacitors, the same way, guys, and tie them and bring it here instead of these condensing units. Same way. You're going to see how we're going to connect them in less than a second here too. This is when you parallel. When you parallel, everything has to be the same. We talked about that one because by now you're doing a lot of parallel video for a chat. So I'm going to talk about the couple of tables that we use, guys. Voltmeter connection, capacitor on the line side, load side. Here's the dielectric, Karen, a copper plate at the top and the bottom, and in between some type of an insulation material that will make a capacitor. Testing your capacitor, ohm meter, and a high pot and so forth. Here's how the condenser unit looks like, Adam. It's a machine that, can you guys see the rotor is running, nothing connected to the rotor. All what you're doing is rotating to correct the power factor. Here's how your capacitors, guys, look like, a capacitor band. Can you guys see all these capacitors connected, different capacitor going to different loads to correct the power factor. So when, I know you guys are not engineers, but the next level, there's a lot of people will be more than happy to make you a drafter, Adam, for the rest of your life. You know, this will move you to the next level. Start sizing capacitors and so forth. Adding all these capacitors to correct to the power factor with different controllers is a big deal, and it's not hard. So that's, see, can you guys see the bank? 1, 2, 3, 4, going, looks like each one of them, the 3 of each, going 3 sets, going to 4 different loads. Okay, here's what I would like you guys to pay attention, because I want to be using this one, please. Why can't I rotate? What do I need to do to rotate this one? I hate that one when I can't rotate it. Okay, cancel. No. Cancel, I don't want, yes. I lost that. Okay, so I think it was here. Okay, so that, can you guys go to the table, please? Because I'm going to be using it in a second. Everybody, please open your book and go to this table. So, I can't, why can't I rotate this one? You show. I don't want to show. Can't. Okay. I hate it when you can't. Okay, so when you guys go there, this is what we're gonna be. I'm just gonna. I want you guys to look at it. Okay, so here's what. Sorry, I can't explain it. Here's your original power factor. That's your original power factor. Original. This is corrected. Corrected power factor. So Adam, when you say go find, if your power factor is 50 and you need to correct it to 87, then your multiplier that you need to use in the table is 1.165. We're going to be using this table, guys, in a second. This table will get you the multiplier that you need to correct for the power factor. Everybody got that? This is a great table to use to get you the multiplier that you need. And I don't know why I can't switch it. But so you can see the most important thing, guys, on this side, on the top side, is what you correct for. And this here is the original power factor. So on the test, when I tell you guys, go correct for a power factor 90, and the original power factor was 60, and go correct to 90, right? This is corrected. This is original. So when I say go correct it, I'm going to go all the way up to here, and your multiplier M is going to be 0.849. Is that 0.849 or 0.849? Everybody knows how to read this table. Can I have thumbs up because it's so important how to read this table? Here's the original power factor. We'll be using it in a second, guys. Here's the corrected power factor. Here's the multiplier that you need to correct. Everybody knows how to read it? Yes? Adam? Good? Okay. So that's the corrected power factor. That's how you read this table. You typically start correcting, guys, with 80 or more. You want your power factor list. Typically, that's what the table is. But typically, the correction starts right here. That's where you want your correction to be, right? 90 or more. So if you correct to 90, you are close enough. Okay, so that's the first thing I would like you guys to go. The second thing is these two tables. Please, if you pay attention to them. So these tables, my friends, talk about the different frames. Okay, let's talk about the first one, guys. Okay, very easy. But I would like you guys to know how to read it, though. Look at this. Oops, here you go. So if you have, the first thing you need to do is this correction is for a power factor. Come on, here you go. There you go. U frame. There you go. Good. So I have first, if I tell you guys it's a U frame, it's made a U frame. The correction is between 93 and 97. This is for a 480 system. If I ask you, Adam, the 100 horsepower motor, what size, and it's running at 1200 RPM, what's the size of the capacitor that you need to correct the power factor for this guy? No calculation needed. The size of the capacitor is right here, 25 kV. Everybody knows how to use this, guys? Very simple. Let's go take one more example. Suppose I have a 20 horsepower, these are horsepower, at 480. This is for a 480 system, 480 volt system, okay? Derek, pick a speed that you want to pick any speed. 1800. I'm going to run that baby at 1800. Typically on the test, I will tell you that, which speed is. Okay, what size capacitor, gentlemen, do we need? 5 kVAR. KVA. So these tables, guys, somebody have done this math for you. That's how you correct for motors. Does that make sense? So this table is for 480 U frame. Right underneath it, Karen, right underneath it is the T frame. The T frame. Yes, U frame, T frame. Design them. So if I tell you U frame, you go to the top. T frame, you go to the bottom. Same thing, guys. I have the 20 horsepower. We're going to run them at 1800 RPM. Here's my KVA, KVR. Everybody knows how to use this table? Can I have thumbs up, Chad? That's what I'm going to be doing in a second here with you. This table is, guys, is the last thing I'm going to do about this table. This is for 480. If your system is 208, can you, Adam, can you go right here and highlight this one for me, guys? Right in here. If your system is 208, you have to go multiply. You have to go multiply by right time here by 33%. You have to increase these values by 33%. So you take this and multiply it by 1.33, and that will get you the correction for a 208 system. The table is made for 480. If you're correcting for a 208, they up it 33%. Okay. Any comments, guys, about these tables? Any comments about these tables? So these are what we're going to be doing in a second here when we do the calc. The last thing, guys, is another table that you have that gives you the standard sizes of capacitors with all the calculation done for you. So this table will give you somebody smarter than Chad have done all these calculations, so you don't get bugged. So let's just say a 480 system. Let's just say I have a 10 kVAR capacitor. Can you guys see that? The full load amp of this baby is this. Normal full load amp at which voltage? The normal full load amp, guys, for the 480 is right here, 12 amps. The conductor size is number 12. The fuse size is 25. The disconnect is 30. So they did the calculation for you. Now, how dumb is that? I mean, it's just everything is done for you. I don't want you to use these, guys. We're going to do our calculation, which is similar to this. Cool? Everybody knows how to use this table. Now, Karen, suppose that the voltage that you're burning your equipment at is 208, is 600. This becomes, these numbers are your numbers, right? Now, Adam, suppose your voltage is this value, so these will be your number. Yeah, thumbs up, Chad. We know how to use this based on the voltage. Cool. Any comments, guys? Any questions? Any comments? Any questions? So, Derek, I'm going to do a calculation, guys, and for the 10 kVA, and I want you to do the calc based on the code. If you come over here and find the different values, please use the ones I'm going to do. But typically, these are standard industry. The calculation have been done for you. So what they did, Karen, here is to size the wire, guys, to size typically these three, they use 135% of the full load current. Any comments, guys? Any questions? Any comments? Any questions about these tables? These are the most important tables I'm going to be referring to in less than a second here. Matt, questions, comments? I know you didn't do the capacitor correction with us. For the rest of you guys, I know you did it a year ago. You can go review the impedance and what's not. I don't want to bug you with the impedance. We can spend 3-4 hours on studying impedance. What I would like you guys to know is the calculation I'm going to do in a few seconds here. Know that we can correct power factor with capacitors and synchronous motors, and this is how we size them, and there's a bunch of tables we can use. Am I making sense there?
Yeah.
With these capacitors?
Of course, just out of the book, just to.
Yeah.
I was kind of going on with you.
Yeah, good.
For one of the ones I asked, said that 1 horsepower is equivalent to 746 volts or watts.
What?
But a 1 horsepower, 200 volt single phase motor, according to table 10.2, has a current of 9.2 amps, and they want you to explain the discrepancy.
The full load, yeah, because of the watts. Yeah, when you have a motor, the watts is what make the motor work.
Yeah.
The full load current in the table is typically for safety, so they add a little bit on it. So if you look at the full load amp of a motor,
Actually, just the true power, it's not the apparent power, though.
because of power factor. So for example, if you have a motor, just take a motor here. If you have a motor that have 10 amp full load current, right? If you have full load amp, full load current from the code typically would be say 12 amps, right? So the nameplate says 10, but the code, you go to the same horsepower, same voltage, give you 12. Why? They take into consideration the low power factor and voltage drop. So when you size your conductors, you size them based on what? This. So you're always safe. Does that make sense? So that they give a safety caution. Any comments, guys? Any question? Good one. Any comments? Any questions about these? So that's basically what I would like to. So in a second, Karen, I'm going to give you guys 5 minutes, and I would like really to go over the calculation. The calculation is very simple. Otherwise, I wouldn't do it. I want to just hit it right after because it's related to capacitors. Hopefully, as we calculate math, it makes more sense. We have 4 examples to do calculation for capacitors. So why don't we guys have, I'm going to be using these tables, so please follow up with me when I go to this table, blah, blah, blah. That's the table that we're going to be using. Shall we? Let's take,
I got something I wanted you to look into.
okay, let's take 5 minutes, 10 minutes, guys, and we'll jump into the second part.